Let's begin. We will start today on comparing two populations, or also what we call two treatments. So when I give you in the quiz next time and say, okay, consider these two treatments, don't tell me I haven't defined treatments. Okay, we'll explain that in a second. Consider two populations or two treatments. You might ask, why are we going to compare two populations? I'm glad you asked, so I will explain this. Now, at the end of this chapter, you'll be able to construct a confidence interval, I hope, for the difference between two population means. Again, you'll ask, like, why do I need to compare two population means? Like, am I comparing, like, head circumference and heights? Of course not. That's not what we're looking at comparing, okay? We're going to be comparing things like before and after a treatment is applied to a process, okay? Before and after adding a gasoline additive to your car. Is that going to improve your car efficiency? Before and after something is done. So it's essentially you're comparing the same thing before and after you've done something to it, okay? We'll be able to do that when samples are independent with a known population standard deviation, which is a silly case. When samples are independent with an unknown sigma, you'll be able to construct a confidence interval when populations are dependent, and this is going to be an interesting case to look at. Confidence intervals for two population variances, not just the means, and when we can pool the data and what that means. Okay, I'll start with an example. True story. Okay, finally we get to some real data. You always want real data. Okay, so this is real data. Okay, what is this data? Right, this is data from my house. Don't tell anybody, okay? I want people to still come and visit my house. No, this is data from my basement in Sandy, okay? Sandy is particularly sandy. The soil is very sandy, and there's a lot. We're like right close to the granite district at the Little Cottonwood, and granite has some radioactive elements to it, so it produces radon gas. Utah has a lot of radon, by the way. If you live in a basement, if you're renting a basement, I told you last time, crack a window open, put a fan, or get a radon monitor, because in the long term, it could cause lung cancer. The interesting statistic is that Utah is one of the lowest smoking populations in the nation, yet it has one of the highest, I think, second or third lung cancer rates. The only explanation is radon exposure. Okay. Most older homes don't have any radon mitigation system or like ducting into it. So we were spending a lot of time in the basement. That's what I'm putting my arcades, not my guitars. So you don't know where I had my guitars. So you cannot come and steal my guitars, but yes, they're there. So we're spending more time there. And obviously for the sake of the kids, I'm disposable. I'll get exposed to radon. I have 10 years anyway. So, but for the kids, I want to make sure that they're not, not exposed to this early on. So I got this radon monitor. It's a great little radon monitor called Radon Eye. It's certified, well calibrated. Got it off Amazon. It's like $175, but it provides continuous radon gas monitoring. Okay, and it takes a sample from the air every 10 minutes and gives you an average every hour. Okay, so up to a year, and then it continuously continues. So it stores 1 year's worth of data, which is 8,760 hours. Okay, now since I bought it just around over here October, I would say 2023, somewhere around October 2023, I started monitoring the y-axis, which is the radon level. It's measured in picocurie. So Curie is the unit for radioactivity. She discovered, radioactivity. So picocurie per liter. So how many radioactive units of exposure are you exposed to per liter, right? So per liter. So your room might be, 800, 1,000 liters, right? So you can guess then how much exposure you're at. And you want to make sure you put your monitor near the breathing zone. So you don't put it on the floor, you don't put it in the ceiling. You put it kind of right at desk level, like here. So I have it set at this height. So it's kind of exposed to, I'm breathing, so I'm inhaling this air, right? So I put it at this level. So if you decide to make a measurement like this, don't put it on a wall, put it in the middle of a room. And it's been continuously monitoring since October 2023 until like just around here. So this is September 2024, 09, and then October. So that's 1 year's worth of data, okay? And then, you know, I saved this data, and then so this data is up to actually September 23rd, 2024. Why? Because that day I saved the data, and what did we do? We installed a radon mitigation system in our home, okay? We installed a radon mitigation system. Now, since we installed it, I have data until today, which is March 7, 2025, right? So that's today. Called my wife this morning, send me the data, I need it for the class, otherwise we're all gonna fail and it's not gonna work. So she rushed, you know, called the president, got the data and sent it to me. So anyway, so this is the data. It's not, this is still 1 year, but some of this data is part of the data above, right? Because this data here, you see there's March 2024, April, May, which is part of the data above, okay? Now, radon is heavily influenced by weather systems and weather patterns, and whether there's a storm or not, because higher atmospheric pressures or lower fronts, they either push the gas out of the soil or it retracts back depending on atmospheric conditions. And you notice these peaks, like, you know, there was one day I had 6 picocurie per liter and then getting 25 peaks, right? And these peaks were scary. But then as you approach the spring and summer, it stabilizes a little bit. Then you go back in winter. But guess when I'm spending my time in the basement? In the winter, right? Because we're like hunkered in, we're not outside. So I'm going in the worst time of the year for radon. I'm spending my time being exposed to radon. Hey, you know, now I want to smoke on top of that. No, but like, you know, it's like the worst time to be in the basement. It's when the weather outside is bad and it's causing more radon gas to come into the basement. Now, sandy is sandy. There's sand in the soil. It makes it porous and easier for the gas to come in, okay? Now, if your slab, your concrete slab, the basement floor has cracks in it, you should start by sealing those cracks, rip out the carpet, seal all the cracks, make sure, you know, you reduce the points of entry for the gas. Or if you're looking at a house, that's one thing you want to look at. A radon mitigation system, you buy it when? You buy it in the summer when it's low, because they give you like a 50% discount. Usually costs $2,000. I got it installed for about $1,000. They sent me a coupon. I called you, yep, yes, let's install it now. So, you know, they came and I could see a drop, right? So you could see that, you know, things were all over the place, and then whoosh, it dropped, right? And yeah, it's doing something, you know, thank God. I'm happy with that. But is it statistically significant? Okay? Is it statistically significant? That's an answer that statistics or statistical analysis, or this chapter in particular, is going to answer. Okay? One more data point. The line, the horizontal line in red, is the concern level set forth by the World Health Organization, which is 2.4, which is the alarm level, 2.4 picocurie per liter. Sometimes they set it at 2.8. The EPA sets it at 4. Nobody knows. What I know is, like, I want it to be 0. Okay, I don't want any, you know, radon in my base, or a minimum level of radon. All right. Now, okay, so I said these graphs share is like this portion is actually part of the upper graph. So in fact, this is the same data as the graph above, right? Because I'm continuously monitoring, and this is the same data, but it's like, why doesn't it look the same? Why is this peak here bigger than that peak over there? This peak should be that second peak over there. This first peak should be that first peak. Why are they different? Because I made a mistake in presenting these plots. I didn't use the same scale on the y-axis, right? So I'm going back to descriptive statistics, okay? So this would be a bad way to present this plot, because it gives the impression that this is much larger than the other one, or as large, where in fact it's not. Because the scale here is up to, what, 25 picocurie per liter, 30, 25, and the other one is, what, 64. So to better present these plots, I need to make sure the y-axis is the same. That's what it should look like, at least if you're presenting it to be consistent, right? And now you can see, like, this peak corresponds to that first over there, this second peak is the second peak. They're exactly the same, right? Because I use the same y-axis. And then you see a more dramatic plateauing here, or drop in the data. In fact, I cannot see anything here. So this is also bad, because if you're looking at it, like, oh, this is just a flat line. It's not a flat line. There's a lot of oscillations over there. Okay, so if I want to do this even better, I can use a log scale over here to rip this apart, or I can just shrink the y value. Anything above 10, as far as I'm concerned, is bad. Okay, so let me make the scale from 0 to 10. So if you make the scale from 0 to 10, you see a little bit more of how the data is all over the place. And then you can see that, okay, these data are the same as the other data up here, right? And this is after the mitigation, this vertical red line, right? So you sudden drop, but it still peaks. Sometimes goes up to 2. Here it went up to 3.6, right? So it's still trying to go up. There's storms and things going on, right? So how can we make sure that the treatment works? What is the treatment here? Is applying a radon mitigation system. Okay, so I have two populations now, or two samples from my data from radon collection. We'll talk about that in a bit. And how can I make sure that actually my radon mitigation did actually drop the radon exposure for me? How can I be sure of that? Well, you could say, okay, from my first population, I have a mean value mu1, or call it sample 1, okay, mu1, and a second population after mitigation is mu2. So I want to think of the population as all radon levels across all days of the year, across all years of my life. That's the population of radon in my basin, as long as I own the house, or forever, okay? So what I've collected is actually just a sample for a few months, right? Out of those many, many years and days and hours of the true population of radon in my house, okay? So think of that as the population. It has a mean value of mu1, and the other population after mitigation, it has a mean value of mu2. So obviously the difference between the two populations, mu1 and mu2, is one way we can compare these populations, right? So if mu1 before mitigation was high, and mu2 after mitigation, if that difference shrinks, right? Or then I made a big difference, right? Or if it stays the same, sorry. If mu1 minus mu2 is a small number, it means I made no difference, because mu2 remained as close to mu1 as it can, right? But if that difference is very close to mu1, it means my mu2 is very small, or the population small. Then that difference can tell me something. The point is that difference will tell me something about whether my treatment worked or not. Now, obviously, we don't know the population means, so we need to estimate the difference from the samples. Okay? So we start by defining two samples are independent, okay, from two populations if the data from the first sample are not connected to the data from the second sample. Two samples are dependent if the data from both samples are systematically connected, or we call them paired. Okay, so let's think about this for a bit. Is my radon data connected or not? Pre-mitigation, after mitigation. Why is it connected? Why it should be connected? Ashton.
Because even though you have a radiation sensor there, you're still taking samples from the same house and location.
Same house, same location, agreed. And in fact, I need to make sure that I'm comparing samples from the same days and the same month, right? And even the same weather. Now, I'm assuming weather is roughly the same, but every data point from after mitigation needs to be consistent with the conditions of prior to mitigation. I cannot grab a sample from the summer and compare it to a sample from the winter. That's not fair, because you saw that the samples in the winter have a much higher spread, right? Much higher mean too, than the samples in the summer, right? So in fact, my data is connected here. This is an example of paired data, we say. Samples that are dependent on each other, okay? In fact, I need to exclude these points and compare these two samples at the same day, the same hour actually. You need to make sure that as you process your data, they need to be as close to each other as possible. Another example, you get a gas additive to your car. You drive your car for a month, okay, same driving conditions, you're commuting from home to work, etc. And then you monitor your fuel consumption, okay. Then you add the gas additive, okay. You need to do the same thing because it's the same car, and you need to make sure you drive the same road and you make the same stops because these data are connected because you're using the same car. Okay? Now, if I'm not using the same car, if I'm using different cars, what I would do, I would grab a sample of 5,000 cars without the additive, 5,000 cars with the additive, and then do a comparison. I don't care how their driving conditions are. Okay? Then that would be independent because it's not the same car, it's not the same conditions. The setup itself is not connected to each other. But here, because I'm sampling in the same house or I'm sampling on the same car, the results are connected because I'm using the same car. I'm using the same house. Pay attention to that. Now you can be fancy, you're reading a study, well, the data is connected. Why did they assume it's not connected, right? It's not paired. Or when you're looking at a study, you say, we pair the data according to hours or something. You're like, okay, that makes sense now because the data are connected. We're going to leave that till the end of the chapter because it's the hardest piece, because you need to look at every data point, take the difference, and then average things out. It's a little bit more involved. So for the radon equivalent of independent samples, what if we had 2,000 of these monitors scattered around the city? And then I'm going to choose half of the homes, so 1,000 homes without a radon mitigation system, we're going to put a sensor in them. And 1,000 homes that have a radon mitigation system, we're going to put the same sensor in them. Okay, and then what if then I monitor the sensor reports an average over the entire year? So I got 1,000 averages for the entire year without mitigation, and 1,000 averages with mitigation. Then those samples are independent. Because I didn't use the same home, and I didn't lock in the weather. I averaged it over the entire year. Okay? So that would be a case of the radon system with independent samples. Okay? Excuse me. If I was sampling in my house, one in the basement and one in the upstairs, you might say they're independent, but the weather is still locking things in. Okay? Because the same house is responding to the same weather. I have to make sure I match the same weather, unless I take averages. Okay? Okay, so that's where comparing populations becomes important. It's a treatment before and after. You apply treatment. Think of a medical treatment. Before you take your pill, after you take the pill. Okay? So what is it doing? Is it improving the outcome? And we need to make sure that our estimate on average, or our estimate of the mean change and the mean deviation, we have certain confidence in it. Okay? So we will start with comparing two population means. So now we're not comparing one mean, we're going to compare two population means. We're going to assume sigma is known. Again, that's the simplest, just to show you how to do the math, like we did previously. But independent samples, because independence makes things very easy mathematically. Okay? We start with, as usual, a point estimator. What is the best point estimator for the difference in population means? Is going to be the difference in sample means. Just the same way that the point estimator for a single population mean was the sample mean, the point estimator for the difference between two population means is the difference between two sample means. The nomenclature we will use is population 1 and population 2. Population 1 has parameters mu1 and sigma1. Population 2 has parameters mu2, sigma2. But sample 1, we're going to call them x, and sample 2, we're going to call them y. I don't want to call x1, x2, because x1, x2, x3 are going to be the sample values, and y1, y2, y3 are going to be the sample values from the other population. So I'm not going to use 1 and 2 for the samples. I'm going to use x and y for the samples. Okay? And then size for sample 1 is n1, and size for sample 2 is n2. And then the simplest unbiased point estimate for the difference between the two population means is going to be the difference in sample means. Okay. Now, the same way that we thought about single populations, there's an error in our point estimate. We built a confidence interval. Let's do the same for this difference. Okay. But before I do that, I need to remind you and make some definitions on math. Okay, because there's no way around it. We have to use some math, right? Remember, the expected value of some function of the random variable x, any random variable, okay, sample mean or whatever, is defined by this integral from minus infinity to infinity, h of x times your PDF, f of x dx, right? So that was basic definition we did. What I didn't do last time is talk to you about some of the properties of the expected value. From here onwards, we're going to use the symbol e to designate the expected value instead of writing the integral every time, because we're going to do calculus and algebra. We're going to do algebra on e itself. Okay? So for example, the expected value of some constant times the random variable is simply that constant times the expected value of the random variable. Right? You can plug that into the integral. If you multiply the integrand by a is a constant. You can pull it out. It becomes aex. So e of ax is equal e of x. Okay? The expected value of a linear combination of two random variables, ax plus by, is equal to the linear combination of expected values of the random variables, e of x plus be of y. Okay? So no more integrals, but you can verify this with the integral, right? Just split the integral, because the integral is a linear operator. It applies linearly. Okay. Now, the expected value of the product of two random variables is not equal to the product of expected values of random variables. We're not going to do this in the homework. You're going to do something similar in the homework, because this is a little bit involved to prove. We don't have the tools to prove this. This requires what we call joint probability distributions. We don't have the proof to do this. But know for a fact that the expected value of x and y, so you have two PDFs here, right? X times y, so that integral becomes a double integral, becomes very complicated. Know that the expected value of the product of is not equal to the product of expected values, unless they are independent. Independent samples, okay? If x and y are independent samples, then we can say for a fact that e of xy is ex times ey, because they have no joint probability, so there's one extra term that disappears. Okay. Now remember also that the mean value was simply the expected value of x. And one thing I didn't define last time was var of x, which is the variance. Okay? Var of x is nothing more than the expected value of x minus mu squared. Okay, so we call that one of the central moments. Okay? Now, if you expand this, so x minus mu squared is x squared plus mu squared minus 2 mu x. And then by linearity of that operation up there, that becomes e of x squared plus e of mu squared minus 2 mu e of x. But e of mu squared is a constant. E of mu squared is mu squared. Mu is mu, e of x is mu, so you get minus 2 mu squared plus mu squared, so you get e of x squared minus mu squared, just a little identity. Okay, that the variance of x is either this or e of x squared minus mu squared. Okay? Okay. One more identity that's very important. So remember that e of xy is not equal to ex times ey unless they are independent. One more formula, the variance of x minus y, the variance of the difference between two random variables, is not equal to the difference in variances. Very important. Now remember, the variance is the expected value of x minus mu squared, so it gets really complicated formula over here. Unless x and y are independent, then the variance of the difference is the sum of the variances. Ooh. It's not even the difference in variances, it's the sum of the variances. You will prove this in your homework, okay? So you're going to figure it out, okay? It's a fun homework assignment. Okay, and you're going to be using all of these identities that I showed to you here. Yeah, you're going to be using those to prove this. Okay. Today is Thursday. So is that the homework assignment today, right? Or tomorrow. Tomorrow. I had no idea. I thought it was Tuesday. Okay. Okay. All right. So now let's go back to our point estimation. Okay, let's get back to our point estimator of the difference in means. Now, I just wanted to show those formulas of the expectation because I want to be able to say, hey, look, I just presented this to you in the previous slide because we're going to use some of those in subsequent derivations. Okay, so this is the setup, population 1, population 2, samples X, call them X, and size N1, samples call them Y from population 2 with size N2. And the point estimator for the mean, the confidence interval, the confidence interval for the mean, we know it's this, it's X bar plus or minus, right, Z alpha over 2, so this is confidence with 1 minus alpha, and times sigma 1 over square root of N1, agreed, so we just did this. And for the second sample, for the second population, so if you were thinking of these as two separate populations, population before radon mitigation, this would be my confidence interval. Population after mitigation, this would be my confidence interval, right? Well, we did this. Okay. Now I want to build a confidence interval for the difference between mu1 and mu2. Okay, I'm going to call it mu1 minus mu2. So remember that mu1 is between these two values here, and mu2 is between these two values, right? So this is another way of writing that confidence interval. So mu1 is between X bar minus Z alpha over 2 sigma 1 over R square root of N1 and X bar plus sigma 1, etc. Okay? So one might say, why not take the difference between these two confidence intervals, right? If mu1 is between these two values here and mu2 is between these two values, let's take their difference. It's totally legal mathematically. It's two inequalities, I'm taking their difference. Agreed? Let's do that. Okay? So if I take the difference, just subtract them from each other, I get X bar minus Y bar. So I get mu1 minus mu2 is between X bar minus Y bar plus and minus Z alpha over 2, sigma 1 over square root of N1 minus sigma 2 over square root of N2. It looks similar to our original formula, right? Z alpha over 2 sigma over square root of N, right? It looks similar. Right? Wrong. This is the wrong formula to use. Bad idea. Bad, Tony. Bad. It's the bad formula to use. Bad mistake. Okay? I'm glad I made a joke, made you laugh. Okay? It's like, all right, so why is this wrong? Why is this wrong? I'm going to step back and go back to the single population confidence interval. Okay? So this confidence interval, I want to rewrite it in terms of more generic quantities like expected value, variance, okay? Because those are not specific to a particular, they're just generic, variance of a variable, right? So I want to try to write this in terms of the variance or expected value or something like that. Those quantities that I define, I told you I'm going to refer to those slides. So those quantities I defined a few slides ago, okay? So this is equal to this, right? I just put the sigma under the square root, so it becomes sigma squared, the square root of sigma squared over n. But what is sigma squared over n? It's the variance of my sample mean. By definition, right? That's the central limit theorem. Tells us that the variance of your sampling, of the sampling distribution of sample means is sigma squared over n. So my confidence interval for a single population, okay, for a single population looks like this. A random variable plus or minus Z alpha over 2, which is also a standard value, right? Times the square root of the variance of that random variable. So any random variable I pick, the sampling distribution or sampling mean, right? I can plug it in here in this formula, right? So instead of X, I could have sampling means of zebras. As long as they're randomly distributed, I can plug them in here, right? And the confidence interval is that random variable, the mean of that random variable, plus or minus z alpha over 2 times the square root of the variance of that variable. Okay, now when we have two samples, x bar and y bar from different populations, then the difference x bar minus y bar is itself a random variable. We have to think in terms of the random variable, not the outcome of the confidence interval after the fact. We have to go back, what is the random variable for the difference between the two populations? It's the difference between the sampling distributions of sample means. That's my random variable. I cannot compute my interval first and then come back and then do the subtraction. No, I have to define a new random variable, x bar minus y bar, because that random variable represents the differences between the populations. Although I'm sampling it separately from each population, their difference is the random variable in question that I need to look at. Their difference has a whole different distribution. And by that logic, if x bar minus y bar is a random variable, how about I just plug it up there? So if I do that, I should expect this to be my confidence interval. X bar minus y bar plus or minus z alpha over 2, agreed? Times the square root of var x bar minus y bar. If I develop a theory that says for all random variables, sampling distributions of sampling means, this should be the general formula. X bar is just, all I care about for x bar is it being a sampling mean random variable. Then I can plug in place of it whatever I want. I could have x bar minus y bar minus z bar. I can have 17 distributions. This should be the interval, right? So now when you take that, and remember the formula, var of x bar minus y bar, if they are independent, it's equal to var of x bar plus var of y bar. That should be my interval, not this one. You will commit a huge error if you take the means and subtract them, if you take the confidence intervals and subtract them, versus, no, you're going to define a new random variable of the differences, and we're going to treat the distribution of those differences, and then do the confidence interval on that distribution. That's the correct way to do it. Okay? It's a common trap when we're doing even analysis in numerical methods. Should I take the means and then take the difference? Or no, take the differences and take the mean? We should do the latter, because this is what this is telling us. Because the distribution of the differences is different than the distribution of the means. So you need to look at the difference itself as its own random variable. Oh, there you go. This is my confidence interval for two populations. Mu1 minus mu2 is between x bar minus y bar, this difference of sample means, minus this error, okay, z alpha over 2, since we know how to do it. And simply, I'm going to do square root of this sum over here. So the difference in means in the population is between these two bounds. Okay? We know sigma, and the samples are independent. If the samples were not independent, we couldn't go from here to here. We'd be stuck here. There's another way to deal with this. Okay? I have 2 minutes. Let me buffer. I have 1 minute, and actually, okay, you go. You can go. Thank you. Godspeed. Have a good weekend.